Hi, my name is Alexis, and today my partner Eddy and I will be presenting on the synthesis of Relvar. Relvar is an inhaler that's used to treat respiratory diseases such as asthma and chronic obstructive pulmonary disease. The active drug compound is fluticasone furoate, which is a corticosteroid. This class of steroids are involved in the regulation of inflammation. Relvar is sold and produced by the pharmaceutical company GlaxoSmithKline, which is based in Ireland. The pharmacological response of Relvar involves the glucocorticoid receptor, which regulates the expression of genes related to immune response. Fluticasone furoate binds to a glucocorticoid receptor located in the cytosol of the cell. The receptor then translocates to the nucleus and binds to glucocorticoid responsive genes. The activated receptor complex may then upregulate transcription of anti-inflammatory genes. The complex can also bind to transcription factors in the cytosol, thus repressing transcription of pro-inflammatory genes.
Our retrosynthetic analysis of Relvar, or fluticasone furoate, is focused on the specific manipulation of the functional groups within this region of the steroid core. A precursor intermediate of Relvar can be reacted with bromofluoromethane to substitute the functional group on the sulfur atom for the appropriate fluoromethyl group. The furyl group that is currently attached is a result from the previous reaction. The first intermediate molecule would be reacted with furyl chloride with the intention of functionalizing the alcohol connected to the stereocenter. However, this also happens to the thiocarboxylic acid, so both the oxygen and sulfur atoms are functionalized in this reaction. The first intermediate can be generated from a starting compound, flumetazone acid, by replacing the carboxylic acid alcohol for a thiol using hydrogen sulfide. Turning our retrosynthetic analysis into a forward synthetic scheme gives the following three reactions. Each of these reactions produce high yields that are over 90% and high purity over 97%. This synthetic route was taken from the fluticasone furoate patent, where a few synthetic routes are proposed for the synthesis of the molecule. This was suggested to be the most efficient method of production due to the overall yield and purity obtained with these protocols. The first reaction involves the thiocarboxylic acid substitution of the flumetazone acid using hydrogen sulfide and CDI. First, the flumetazone acid and CDI are dissolved in DMF, and the reaction is placed under an inert atmosphere using nitrogen gas. The mixture is then stirred at room temperature for 4 hours. Afterwards, the hydrogen sulfide gas is added until the reaction is completed as determined by TLC. The thiocarboxylic acid product is then crashed out of solution by using 2-normality hydrochloric acid and water. The product gets filtered and dried, giving a 97.5% purity with a percent yield of 91.3%. The mechanism of the first reaction begins with the deprotonation of the carboxylic acid, which leads to the carboxylic acid attacking the carbonyl within the CDI. This carbonyl then reforms and kicks out an imidazole group that is now a side product of the reaction. The other imidazole group deprotonates the hydrogen sulfide, which allows it to attack the carbonyl of interest, and leads to this cascade of electron transfers that generates carbon dioxide and another of the imidazole side products, along with our product of interest, the thiocarboxylic acid.
The next step of the synthesis involves the coupling of furoate to the alcohol and thioic acid on the 5-membered ring. Thioic acid is dissolved in acetone, then triethylamine and furyl chloride are added to the reaction. The temperature of the reaction is maintained at -5 degrees Celsius. After 30 minutes of stirring, the product crashes out of the solution, is filtered, and dried. The product is obtained in 98.2% purity and 95.9% yield. The mechanism of the second reaction begins with triethylamine deprotonating the thioic acid. Triethylamine can also nucleophilically attack the carbonyl of the furyl chloride, forming a tetrahedral intermediate which will rearrange, kicking off the chloride ion. The deprotonated sulfur may then undergo a nucleophilic attack of the carbonyl, resulting in formation of another tetrahedral intermediate. Since the quaternary ammonium cation is a good leaving group, the carbonyl will then reform and the triethylamine will leave. Triethylamine may then deprotonate the adjacent alcohol. Because the tertiary alcohol is very sterically hindered, it may be difficult for it to attack another furyl compound. Instead, it can undergo nucleophilic attack of the carbonyl of the thioester to form an intramolecular 5-membered ring. The carbonyl will reform, breaking the sulfide bond. The sulfur can then nucleophilically attack another furyl compound. The carbonyl will reform as previously, kicking off the triethylamine group and forming the final furoate compound.
The final reaction involves the fluoromethylation of the thioanhydride intermediate using bromofluoromethane and DMAP. First, bromofluoromethane and DMAP are dissolved in acetone. The solution is stirred and cooled to a temperature between 5 to 10 degrees Celsius for 3 hours. This is followed by the addition of thioanhydride intermediate, while the reaction completion is monitored by TLC. Once the reaction has reached completion, the final product is crashed out by adding water to the solution, then the product is filtered and dried. The final product results in a purity of 98.3% and a percent yield of 97.8%, finalizing the synthesis of Relvar. The mechanism of the final reaction begins with DMAP attacking the outer carbonyl of the thioanhydride, and then the carbonyl reforming and kicking off our molecule as the leaving group, creating a deprotonated thiocarboxylic acid that can undergo an SN2 attack of bromofluoromethane, kicking off bromine, generating our final product and an amine salt byproduct.